So in today's lecture, we are going to investigate the use of metric spaces in the design of approximation algorithms. So metric spaces come up a lot, especially when the problems are related to finding cuts in graphs. Now, before we go to that, I just want to quickly recap what happened in last time's lecture. Uh, we looked at the problem of coloring three colorable graphs. That is, the graph was given to be three colorable, and we wanted to actually find a coloring with a few number of colors. Now, the best we could do, as we saw, was something like n raised to 0.25. And that is close to the best known. And what we used was a SDP relaxation and rounding approach. The formulation of the problem in terms of a SDP was based on the fact that there exists a vector coloring solution for the graph. Okay? And the rounding of this SDP use properties of the standard Gaussian distribution. So today's lecture is somewhat disjoint from last time's, although to note there are very interesting connections between semi-definite programs and metric spaces. However, we'll not be able to cover those in the course. Okay, so the plan for today is to give a quick recap of metric spaces that you've already encountered before, say in TSP or in facility location. And then we are going to look at three problems: the ST min cut problem, the min multi-way cut problem, and the multi-cut problem. All these three problems involve finding some cuts in graphs, of course. The common thread between the techniques that we'll see for this is to view these problems as being in some metric space. Okay, so what I mean by that is the LP relaxation will be formulated based on the fact that these are basically some sort of metric space based problems. It will become clear when I define the problems and their relaxation as to what we want. And we are going to give randomized approximation algorithms uh, for all of these problems. So let me define all the three problems that we'll look at beforehand. And this will give you an idea of how each is a generalization of the one that precedes it. Okay. Our rounding algorithms will similarly be slightly more involved as we move from left to right in this series of three problems. Now, the ST min-cut problem is something that you've already seen. Um, the input is an undirected graph with costs on the edges, often known as capacities on the edges. You have two distinguished vertices, a source vertex and a sink vertex, S and T. Because the graph is undirected, these are basically interchangeable. The output you want is a subset of the edges, such that if you remove these edges from the graph, then you basically disconnect S from T. So this is F over here. The objective, as you would know, is to minimize the sum of the costs of the edges in F. Next, the multi-way cut problem is a simple generalization of the ST min cut problem, where you just don't have two vertices, but you have k vertices. So here's the definition of the multi-way cut problem. The input is the same. You have an undirected graph with costs on the edges, except now instead of two kind of distinguished vertices, we have k distinguished terminals, which I will call S1 to Sk. Okay, the output is the same. You want a subset of the edges. However, the slightly generalized condition is that you want the set of edges, if removed, to disconnect every pair Si from Sj. Okay, so what you're going to end up with at the removal of these edges is something like k islands, where each island contains the corresponding Si. Now, further generalizing this is the multi-cut problem. Now, the input here is going to be a graph which is again undirected with costs on the edges. Now you have k pairs of distinguished vertices Si, Ti for I in 1 to k. And the goal is to output again a subset of the edges such that removing F will disconnect every Si from the corresponding pair. Okay, and the objective, as before, is to minimize the sum of the costs of the edges in F. So the diagram should give you an idea of kind of how these are actually looking like. So clearly, a multi-way cut generalizes the ST-min cut, and a multi-cut generalizes even the multi-way cut. What are the algorithms that we'll see for this? For the ST-min cut problem, as you would expect, we are going to see a completely polynomial time algorithm. Okay, that solves the problem exactly. This is not surprising because you do know from previous experience that you can solve these min cut problems in polynomial time. Here we are going to see a 2 approximation because the problem is NP hard. And finally, for the multi-cut problem, we are going to see an order ln k approximation. Okay, so I hope the problem definitions are clear. Let me go on to actually recapping formally what a metric space is, because we'll use that in order to design the LP relaxations for each of these problems in turn. So you have seen metric spaces before, in particular in the very first or second lecture where we saw the TSP problem, and then we also saw the uncapacitated facility location problem, where both of the problems were actually set up in metric. In fact, we had also seen the k-median problem via local search algorithm, which also used the fact that the points was in a metric space. It was in the very definition of the problem. If you recall, the definition that it used was the following: x comma d, where x is a set of points and d is a distance function, is a metric space if the function d, which takes as input pair of points in x and goes to non-negative quantities, satisfies the following. First of all, d of ij is equal to 0 if and only if I equal to j, where I and j are in x. Next, d of ij is equal to d of ji, which is basically symmetry. And finally, and the most important, is that d of ij plus d of jk greater than equal to d of ik. Okay, this is called the triangle inequality. As you have seen, this is for all ij in x, and the triangle inequality holds for all ijk triples in x. Okay. Now, the condition A in most of our settings of combinatorial optimization problems need not always be satisfied. So you can have points, distinct points that overlap at the same place, in which case at times we might want to relax the condition A because we'll not really use it explicitly in our problems. So a semi-metric, basically a pair XD that satisfies the above, except for point A. And most of the uh, cases that we will be dealing with in our problems will be semi-metrics. Now let's look at some examples of metric spaces. Now, the simplest example, as I've already told you at some point, is the shortest path metric on a graph, where given a graph p comma e and a weight function which goes from the edge set to reals, we have d. So you define the d function to be the shortest path distance between u comma v in G. This case v comma d, as defined above, is a metric space. The only non-trivial thing to check is whether it satisfies the triangle inequality. Now, the second canonical example of metric spaces are just your d-dimensional space with the LP norm, which is called the LP metric space. So this is basically the input point set is infinite, because if you take all of Rd, you can take some subset x comma d, where x is subset of the d-dimensional space, and the distance between 2 points x comma y is given by the LP norm of the point, which is summation I equal to 1 to d of xi minus yi whole raised to p, this raised to 1 over p. So this is also a metric space, and the interesting ones for our purposes will usually be the L1 space or the L2 space. So these are most commonly used, especially the L1 space in combinatorial optimization. And finally, you can also have what is called as the cut metric. This is going to be really important for our purposes. Okay, so the input is a set of points, and say the size of x, the discrete point set with n points, although this is not really necessary. Now the distance function d is specified by a subset. And how does the distance function come into play? Well, based on the subset, we say that for 2 points ds of ij is equal to 1 if I element of S and j element of S complement, or I element of S complement and j element of S, that is, they lie, one of them lies in S and the other lies in S complement, and 0 otherwise. So otherwise means both I and j lie in the same part, either in S or in S complement. Now I claim that this, the distance function given by this, actually forms a metric space. Now the only non-trivial thing to verify in order to prove that this is a metric is the triangle inequality. This is quite easy to verify. Well, you take 3 points. And what we want to show, let's say points are I, j, k. Let us say d of I, k. Now if I and k are on the same side, I, that is d of ik is equal to 0, then the triangle inequality is trivial, because the right hand side of the triangle inequality, that is, we want to show d of ik is less than equal to d of ij plus d of jk for all triples, then RHS is severely greater than this, because both terms on the right hand side are non-negative. But what if d and I and k are on opposite sides? So that's the case where I is here and k is here. So if d of ik is equal to 1, then either one of d of ij or d of jk is equal to 1. Okay, because j has to lie either in S or in S complement. So either the distance from to I is 1 or the distance to k is equal to 1. So this would imply triangle inequality is satisfied. Now using this, what we can view all the cut problems that you have seen as follows basically. So if you have a find a cut problem that minimizes some objective, so you know that since cuts are in one-to-one correspondence with cut metrics, you can do this to saying that you want to minimize slash maximize an objective, okay, where the objective has as its variables the dij's. Okay, so the dij's are the variables subject to the fact that D is a cut metric. Okay. So this is exactly the same as saying that you want to find an objective minimum or maximum of a cut in the graph. So you're optimizing over all such cuts by going over all such cut metrics. Now the relaxation of this is the following: minimum, maximum of objective. You keep the variables same as the dij's. So the objective depends upon the dij variables, which are the distance variables between pairs of vertices, such that, and now the relaxation is that D is any metric, okay, or D is a metric. So that is the only condition, and notice that the fact that D is a metric can be expressed in terms of linear inequalities. Because our triangle inequality was linear, the symmetry condition was linear, and of course the fact that they are non-negative is again just a linear inequality. So let's go ahead and apply the framework that I've just stated here to formulate a LP relaxation for the min-ST cut problem. So the variables here will be the distance variables between every vertex pair u comma v. So these are unordered pairs. Okay, so we'll assume symmetry by default that duv is the same variable as dvu. Okay, now the objective, of course, is going to be the sum over all edges, where an edge is the uv of the capacity times an indicator of whether u and v are separated or not. Okay, subject to, of course, as we had seen, we just want d, the distance function, to be a cut metric. Of course, writing this in terms of linear inequalities is not possible. In fact, it might be possible, but not in a polynomial size linear program. So we're going to relax this, as I said, to any metric, and the corresponding linear inequalities there would be written the following way. So the objective remains the same. Such that, and now what I'm going to say is, instead of d being a cut metric, I'm going to relax it to d being any metric. And that involves us only writing down the triangle inequality. And of course, d of uv is greater than or equal to 0 for all uv in v. Now, an important thing that we have missed when we just call it a cut metric is the fact that we want a minimum st cut, that is, we want to separate s from t, and so the corresponding constraint over here is cut metric that separates s comma t. Now, if it's a cut metric that separates s comma t, it basically means that d of s comma t is equal to 1, and that can just be written here as d of s comma t is equal to 1. Now, if you recall, this is exactly the LP formulation that I had given you in your problem set 4 and asked you to justify why it is a min-cut LP relaxation and write out its dual. So now let's go ahead and design a LP rounding algorithm for this problem. I'll call this as LP1, and here's a rounding algorithm for it. So let D be the optimal solution to LP1. Okay, so the value that I'll use as usual is ZLP1. Now it's going to be a randomized algorithm, so I'm going to select row uniformly at random in the interval. So it's a continuous interval 0, 1, and now I'm going to call Vs to be the subset of vertices that are in SS side of the cut as being those vertices such that d of u comma s is less than equal to 0. And the edges that cross Vs are going to be my set F. Okay. So the point is, the solution to LP1 as written need not be a cut metric, but it is still some sort of metric. So it gives us some indication of what the distances between the points should look like, although these might be fractional values. And now to convert that into an integral 0, 1 assignment, what we do is look at the vertices that are close to S. Okay, so the Vs here is nothing but a ball of radius rho around the point S when viewed as part of the metric space. And the ball is with respect to the distance function d that is output by the LP. So let's do the analysis of this algorithm. Well, we are going to introduce indicator random variables as is to be expected. So xe is 1 if e is in F and 0 otherwise. Okay, so I'm going to fix some edge and I'm going to compute the probability that e is in F, which is basically the probability that x equal to 1. And how do we find this out? So of course you view the points like a metric space. Notice that we are not actually looking at these as vertices of a graph in this picture. The LPS output some distances between the points. So imagine something like this. You have S and a vertex U, and the distance looks like d of SU, okay, according to the value d output by the LP. So I pick a ball of radius rho around S, and that ball is of a random radius, right? Now if you fix an edge u comma v, what is the probability that it is cut by this? Well, assume without loss of generality that d of SU is less than d of SV. Okay, then the edge is cut when rho lies, when this ball radius lies between d of SU and d of SV. Okay. So this implies that the probability that xc equal to 1 is equal to the probability that rho lies between d of SU and d of SV, which is d of SV minus d of SU divided by 1, because the interval is of length 1. Notice that by the triangle inequality, this is less than equal to d of uv. So now using this quantity, what do we get? The expected output of the algo, or the expected cost of the edges cut by the algorithm, is simply the expected value of summation over all edges in E of CE XE, which is summation over edges CE expected value of XE, which we know is less than equal to summation E in E CE d of uv, which is equal to ZLP. So we're not losing anything in the approximation factor, and this in retrospect when you look back should imply that the LP itself give you the optimal value of the min cut. We use the fact that rho is uniformly distributed over here. So this gives us a polynomial time algorithm for finding the min ST cut in a graph. So now let's move on to the next problem, which was a generalization of this, if you recall, the multi-way cut problem. So here's the definition of the problem for multi-way cut, if you don't recall it. You're just given k terminals and you want a subset of edges that separates all of them. Now the LP relaxation for this is going to be a simple generalization of the LP relaxation of the min SD cut problem. Notice that there we had actually written out that the distance between S and T should be 1 for the D variables. Here we'll want that the distance between Si and Sj for every pair ij where I not equal to j is at least 1. So you have, as before, a minimum, a summation over E duv. Again, duvs are the variables, one for each pair, and it indicates whether u and v lie in the same part or not. Notice that now you have k parts instead of just one part, instead of just two parts. Okay, so subject to well, I could put equal to 1 or greater than equal to 1. It's the same thing. You will never have a distance which is greater than 1 because it's not required for the algorithm to function. Okay, so the ij's are in 1 to k, and for all v, and of course you have non-negativity constraints. Okay. I hope the LP relaxation is clear. Let's state the rounding algorithm. Now, unlike in the previous case where you could just take one ball and capture the vertices, notice that here we have got k different terminal pairs. And what we'll do is we'll instead draw k balls, one around each of these terminals. Okay, and each of these will capture some set of the vertices onto its side. Although they all are going to use the same random radius. So let me call this LP here as just as LP. So you have, let D be an optimal solution to the above LP with value ZLP. Like before, we are going to pick a random radius. And now instead of picking the radius in 0, 1, we are going to pick it in the open interval 0, half, where half is not included. We will see in a moment why this is useful to do. We define the sets Vi is U such that D of I, U so, and 4 we return the union of the edges going across each of these cuts. Okay. So if you notice, by definition, each Vi is an isolating cut for Si. That is, it separates Si from all the other terminals. So of course, the union of all of this the output set of edges. Let me call you return the union of the edges crossing each of this, which I'll call F. The output set of edges F is indeed a multicut. So how do we see this? Well, notice that as I said, the random radius row is between 0 and half, right? So the balls that you draw out around each of the terminals are of radius at most half, okay? Which means that the diameter of every ball that we output, every VI, that is the largest distance between any 2 points in VI, is at most, in fact, it is strictly less than 1. Since rho is strictly less than half, if you pick a random radius around something, you cannot have anything or any 2 points of distance greater than 1 within the ball. But then the distance Sj is greater than equal to 1 implies no 2 are contained in the same set, and that kind of proves the fact that the output set of edges crossing the VIs is surely a multicut. Now a small observation to keep in mind in this regard is that if you pick a single vertex u, it cannot lie in two of these VIs. Okay, the reason is the following. Well, what does the solution look like? Well, you have these points separated by some distances given by the LP. You have S1 and you have S2, right? Now, S1 throws a ball of random radius around it. Okay, and now, so let us take a U, a vertex. Now, I claim that U cannot lie also in the ball around S2 if it already lies in the ball around S1. And the reason is simply because we have d of S1 S2 is less than equal to d of S1U plus d of S2U. Now this we know is greater than equal to 1. This implies either 1 or rather at least 1 of d of S1U or d of S2U greater than equal to half. Okay, so of course the ball of radius rho cannot capture U. Now the other point to observe is that there might be vertices U that don't fall in any of the balls. For instance, if the random radius rho turned out to be a really small radius because we are choosing it randomly from 0 to half, then what happens? Then clearly that U does not belong to any of the balls that you will choose around the terminals if U lies at some large distance from each of them. And but that's totally fine because we just define the VIs as before and we count all the edges that go across or out of the VIs. Okay, so according to our definition, such vertices can exist, but they do not affect the algorithm directly. So now with that in mind, let's go on to analyze the algorithm, and we do that the same as before. We'll consider edge by edge analysis. So let's say that edge is UV, like in the ST-mincut problem. We know that only one of the SIs will capture this, if at all, for any vertex U or V. So we'll define the following. S of U is that particular SI such that d of Si comma u is less than equal to half, or rather less than half. Okay. And similarly we'll define S of v is equal to Sj such that d of Sj comma v is less than half. Okay. So either one of S of u or S of v may not exist. Okay, which is fine, as we'll see in the algorithm. So we have a case. So what we want to ask is, what is the probability that edge E is cut? Okay, that is E goes across one of the VIs. Well, of course, it is a probability that there exists an I such that Si captures U and not V, or V and not U. Okay, in this case, you will have that the edge goes across the cut. Now, of course, the only I that can capture U is the only Si that can capture U is S of U, and the only Si that can capture V is S of V. Yeah, according to the definition that we have made over here. So let us consider cases based on what happens. A case 0 is, of course, when both S of U, S of V are undefined, implies the edge is never cut. Okay, that's simply because no ball is going to separate U from V. Case 1 is when S of U is equal to S of V and both of this is equal to some Si. Okay, so there's one single Si which is close to both of these within the radius half. In this case, like before, the probability that E is in F is equal to the probability that rho, and without loss of generality, like before, I'm going to assume that d of Si comma u less than d of Si comma v, right? And this is equal to d of Si comma v minus d of Si comma u, and we'll divide this by 2 because rho is picked randomly in the radius, or rather we'll divide this by half because rho is uniform in 0 half. Okay, and this is without loss of generality. I'm assuming that d of SIU less than d of SIV. And this is at most by triangle inequality, like before, 2 times d of UV. Okay, so that's good. You can see why the 2 approximation is coming, but we have one important case left to tackle. When S of U is not equal to S of V. So let us say that S of U is equal to Si and S of V is equal to Sj. Now, if one of these is undefined, you will see that the probability is at most what we'll write below. Okay, so it's not going to be a problem. Now, the probability that E is in my final edge set basically equal to the probability that E is either crossing Vi or E is crossing Vj, which is basically another way of saying that probability. Okay, I can use an union bound here, and similarly So if you remember, Vi is the ball around Si, which may capture U, and Vj is the ball around Sj, which may capture V. Now this here is the probability that rho is greater than d of Si comma U, which is going to look like, now rho is uniform in the 0 comma half. Okay, it never goes more than half, and d of Si comma U is less than this. So now what is the probability that rho captures this? Rho is greater than d of Si comma U. Well, this is exactly equal to half minus d of Si comma U, again divided by half. Similarly, this is equal to probability that rho is greater than d of Sj comma V, half minus d of j comma V, again divided by half. In both cases, we are using the fact that rho is uniformly distributed in 0 to half. The sum of these two, well, I should write this is a inequality by the union bound. Okay, so the probability that E is in F less than or equal to 2 times one minus d of a comma u, d of a comma v. Now get this just by adding up the two probabilities, and now this less than or equal to 2 times 1 minus d of, well, we do know that d of si comma sj is greater than or equal to 1, right? So I've just replaced this by the LP constraint, and now we can use triangle inequality on these 3 points. Okay, so this is kind of the extended triangle inequality, which you can prove the following, that d of SISJ is less than or equal to d of SIU plus d of UV plus d of VSJ. So you're just using, instead of using it on 3 points at a time, I'm going to use it on all the 4 points. It's saying that between Si and Sj, you have U, V, this, then the distance between Si and Sj is less than the sum of the 3 length path to U and V going between Si and Sj. Okay. So this is not very difficult to see using the usual triangle inequality. So this gives us that the probability that E is in F is less than or equal to 2 times, well, you notice that just transposing the other two terms on the left hand side in this inequality, we get 2 times d of uv. So this implies in all cases the probability that E is in the final cut output less than 2 times d of uv. Okay. So now if we introduce indicator random variables just like in the ST min cut, I'm not going to write that out explicitly, the expected value of the weight of the edges or the cost of the edges output by the algorithm is equal to summation over edges CE, where each edge is UV. You will have expected value of, rather, probability that E is in F, which is less than or equal to 2 times summation CE of UV, which is twice times the LP value. Okay, so this is a randomized 2 approximation. Now you can also have a purely LP based algorithm, a purely combinatorial algorithm that gives you the same result using similar techniques. But this technique of choosing a random radius and analyzing the value of the cost of the edges cut by the algorithm and expectation is going to be useful for our next problem also. So recall the statement of the multicut problem that I told you at the start of the class. The input is a graph and undirected with costs on the edges. Um, and you have k terminal pairs now. So this strictly generalizes the multi-way cut problem. You've got these terminal pairs are called Si, Ti, and the output is a subset of edges, which again we'll call F, such that removing F from the edge set disconnects Si from its corresponding paired terminal Ti. Okay, so the picture that you should keep in mind is the one that is drawn on the right above. And what we'll see is a order log k approximation for this. Again, k is the number of terminal pairs. Now, like before, we are going to write down an LP relaxation similar to the multi-way cut problem with the obvious extra set of inequalities. So the objective is the same. The variables are going to be the same. So I'm not going to specify it again. You want to minimize over this d variables, summation over edges, CE d of UV, where E is subject to the fact that d of Si, Ti is greater than equal to 1. So now the Si and Sj pairs can be close together, but every Si and Ti pair should be separated. And next, of course, you have the triangle inequalities, which states that d of U is less than equal to d of UW plus d of V. And of course, these are all non-negative. Now, what does a solution to this LP look like? Well, you should just think of it again as before as points with some distances between them. Now, in the previous one, the SIs and SJs were close together, were far apart. They had distance at least one. Here, say the S1 and S2 can be close together, but S1 should be far from T1 and S2 should be far from T2. Okay, so the S1 T1 distance is at least 1, the S2 T2 distance is at least 1, and so on and so forth. So just intuitively, how do we go about generalizing the previous algorithm to this problem? Well, as before, we are going to end up drawing balls of radius around the SIs. Okay. Now, the only distinction from the previous one comes in the fact that the balls around, say, S1 and S2 may overlap because S1 and S2 can be close to each other, right? So I draw a ball of radius rho around S1. Okay, and now you see that it might end up containing S2, but we don't really care about this now. We will go ahead and draw a second ball around S2, and now S2 will claim all those vertices around its ball of the same radius rho that are not in S1. So basically S2 will claim all of these. Now if you have a third S3 that is lying over here, it will draw radius 3 ball, radius rho ball, and claim all the vertices in this ball which are not around S, which are not covered already by S1 and S2. So we have this ordering. Now the point to think about over here is why is S1 so special and why it's getting the first preference over here. And so to avoid this, what we're going to do is in fact permute the terminals S1 to Sk randomly and then choose a radius rho around each terminal in the order of the permutation. So I'll introduce some notations about permutations to make things clear. So will be a permutation sigma of the set 1 to k going to give me k numbers sigma of 1 to sigma of k. And how I'm going to think of this is the following. Sigma of 1 is my first number in the permutation, sigma of 2 is the second number in the permutation, and so on until sigma of k is the last number. So using this notation, our algorithm is going to be the following. Well, of course, at the first step, you're going to solve the LP and get the optimal distances. D, and the objective value is say ZLP. Now we'll pick a uniformly random permutation of the set 1 to k, right? So this permutes the k terminal pairs in some way. And now we'll go in order. Okay. So we go to sigma of 1 and we'll define V sigma of 1 or rather V sigma of I as the ball around S sigma of I and rho. But of course this ball might overlap with some of the vertices that are already captured by the previous terminals. So we're going to subtract all that out. So we're going to subtract out minus union j less than I V sigma of j. So it's exactly the picture that I've shown over here, except now that you will consider this in order of the permutation. So you might first go for S3 and then S2 and then finally S1 if your permutation was 3, 2, okay. And finally, of course, each of these V sigma i's are isolating cuts around S sigma of I, and so you will output the union of the boundary. Okay. So all the edges that are crossing out will fall in your final multicut. Now, the first claim, of course, is that the above algorithm outputs a valid multicut. Define this as F. And the proof should be obvious. It's kind of similar to the proof I'd stated for multi-way cut, although there actually it is much simpler because you do know that the balls are disjoint around each SI. Here that's not the case, but still suppose again some ball contains both SI and TI. The height of the ball is less than 1, but D of SI greater than 1 implies they never fall in the same V sigma of I. In fact, this first statement here is redundant. So consider some ball chosen by the algo. Okay, so some V sigma of I, even if you consider the diameter is less than 1, but the distance between the terminal pairs is at least 1. Okay, so now given this, that it's indeed a valid multicut, let's go ahead to analyzing uh, the performance of the algorithm. Yeah, and for this again we are going to go edge by edge. The main claim that we'll prove is the following. We're going to show that the probability for all edges, the probability that the edge is in the final cut is less than equal to 2 times the kth harmonic number times the distance on the edge. I'm going to call you E as UV. And what is the kth harmonic number? If you are unfamiliar with it, this is just the sum from I is equal to 1 to k of 1 over I. Okay. So on until 1 over k. And it's not difficult to show that this is order of natural log of k. In fact, it's very tight. It's theta of log k plus minus 1. And it should be clear at this point using the main lemma. Plus linearity of expectation. The expected value of the algorithm or the performance of it is the expected value of the cost of edges f, which is summation over all edges 3 times probability that is f, which we know less than 2 times summation over e v, and this is ZLP, so we get a log k approximation. Now let's go ahead and prove the main lemma. So this is what we want to prove, and what we're going to do as before is to go edge by edge. So you fix some edge E, right? And now U and V are 2 points in a space, in the space like this. You have U and V, some distances with all the remaining points. Now what I'm going to do is I'm going to think about a certain terminal pair, that is a ball around some SI, as capturing or cutting this edge one by one. Okay, so now what happens? Okay, first let us say that we had a random permutation of S1, S2 and S3, and S3 turned up first, in which case you would say, okay, what is the probability that S3 actually cuts this edge? Well, S3 is closer to U than to V. Okay, so of course S3 will cut this particular edge if the ball around it captures U and not V, right? Now if you look at S2, okay, suppose S2 turned up earlier in the permutation, then S2 would actually, the ball around S2 would end up cutting this edge if it captured V and not U, because S2 is closer to V as compared to U. Okay. So it depends on, first of all, which terminal comes up first in your permutation between of 1 to k, and secondly, what is the random radius that is chosen. Okay. So both of these come together in a very nice way. And so to capture this, what we'll do is introduce some notation for a terminal SI. Let Li is be the minimum distance to either of this pair. Okay, so it's the minimum of D of SIU or D of SIV, and of course Ri is the maximum of 2. Okay, so for S3, the minimum distance is to U and the maximum distance to V with the corresponding distances, and similarly. So, of course, an SI has a chance of cutting the edge UV if the random radius lies between Li and Ri. Okay, that's what we have seen. Now, I'm going to kind of assume without loss of generality. This is just to avoid notation becoming more cumbersome, that L1 is less than equal to less than equal to 1 Lk. Now, here's the deal. What this arrangement means is that it's not just enough for, say, let us take S10 here. It is not just enough for S10 to have its radius within this range, that is within L10 and R10, in order to cut the edge UV, but also it should do so without any of the previous ones being cut. Okay, that is without any of the previous terminals already cutting this particular edge. Because if they had cut this particular edge by capturing one of the vertices, then clearly the edge crossing over, the edge UV is counted in that particular terminal's count. So, for example, we count the given edge, that is UV, as belonging to the boundary of S10, that is the ball around S10, it captures some vertices. Only if, so of course, we should have that the random radius lies between L10 and R10, which is basically as illustrated over here. You have S10, which captures one of the two vertices. Okay, but also it should be that the terminals which have lower distance do not capture any of these vertices. So the second equally important condition is that S10, or rather 10, occurs before 1 to 9 in the random ordering. And you can convince yourself that if any of these 1 to 9, S1 to S9, were ordered before S10 in the permutation, then it would never be that S10 can just take up one of these vertices and not the other. Okay. So in general, the probability that E is in F is the union of the probability that right. Now this is a union bound. I'll go from I equal to 1 to k, or rather, yeah, I can use I instead of j over here. And say that this is the probability that, well, I'm just going to combine the two events denoted by A and B that occurs before. So rho is less than equal, greater than equal to Lj, rather L. I'm just going to write down the union bound explicitly, and because it's just a permutation, I can say the probability that the random radius rho lies in the following range. You have it between Li and Ri, and I comes in the ordering sigma before 1 to I minus 1. Okay. So not only should the radius lie, but it should be able to capture it before the vertices are captured by the smaller balls that might occur. So now At this point, you notice that these two events are independent because the step of drawing a random permutation was independent of the random radius that was chosen. Now I can just multiply these two. So this notation basically means I occurs before 1 to I minus 1 in the random permutation sigma. What does this give us over here? What is this probability? Well, this is just Ri minus Li by half, and this because rho is chosen uniformly at random, and the probability that I occurs before 1 to I minus 1 in the random permutation is exactly 1 over I. Now what is Ri minus Li? Notice that Ri minus Li is by definition just d of SIU, d of the absolute value, okay? Because either of these can be Ri or Li, but once you take the absolute value, it turns out to be this. And by the triangle inequality, this is less than equal to the distance between U and V. Okay? So substituting this back, what we get is the probability that UV is in the final set is less than equal to summation I equal to 1 to k of d of UV times 2 times 1 over I. Now d of UV is common out, so what we get is 2 times d of UV times summation I equal to 1 to k 1 over I. And if you notice, this is exactly the kth harmonic number that we were looking for. So this proves the main lemma. And using the main lemma, we had seen how we prove our initial claim. So that is the multicut algorithm, and log k is the best known for the multicut problem. And in fact, the LP also has an integrality gap of omega log k. Now, this is not the case for multi-way cut. The algorithm that we saw was a 2 approximation. The best known algorithm is actually a 1.3 odd approximation. Let me write that here for the multi-way cut. Best algorithm 1.3 approximation. And you can actually get a better than 2 approximation. You can get a 1.5 approximation using a stronger LP relaxation. And this is in fact there in the textbook. If you're interested, you can go over it. So this lecture was kind of an introduction to the use of cuts and metrics in the design of approximation algorithms. And this is kind of just the starting, because a large number of problems can be expressed in a similar form, and the techniques to solve this do in many times involve interesting tools from mathematics, like embedding metric spaces, going from one metric to other with lower distortion, which is a purely mathematical question, and these kind of questions are useful in solving or giving better approximation guarantees for combinatorial algorithms. So that's all I want to cover for today, and I'll see you next lecture on Thursday.